I'd like to briefly talk about our different types of properties of intermolecular properties. A quick reminder: our intermolecular properties, ranging from weakest to strongest, are London dispersion forces or dispersion forces, depending on how you talk about them. We have then from there dipole, induced dipole. You have dipole-dipole. You have hydrogen bond. And you have usually ionic. Or maybe around the same place, ion dipole, and then ionic. All these would fall under the scale of van der Waals. Van der Waals was the generic name for all intermolecular attraction, the van der Waals attractive forces. But London dispersion force, all this has to do with opposite charges attract. The larger the opposite charge, the greater the attractive force. So ionic, which is usually a full positive and a full negative, sees the greatest degree of attraction. London dispersion forces, which is which every molecule has, is the one that is largely prevalent in nonpolar, in that this one is also called instantaneous dipole, induced dipole, where one molecule accidentally gets a dipole from electrons moving around, and that dipole forces another dipole in the next molecule and creates a small fraction of attraction. You have enough of these instantaneous induced dipoles, and you suddenly have something going on. So London dispersion forces are controlled by size, shape, kind of number of electrons, and polarizability. How easy is it to move those electrons around? Like iodine is very polarizable. So iodine, I2, is a solid, while Br2 is slightly less polarizable. And so Br2 ends up being a liquid. And chlorine and fluorine are even less polarizable than the other two. And so they end up being gases at room temperature, even though they all kind of have the exact same properties, the exact same shape. The difference is the size and number of electrons and essentially polarizability. That iodine, it's easier to move the electrons to one side or the other, and so induced dipoles and instantaneous dipoles are easier to form. Whenever I talk about just a straight up dipole, we're talking about a permanent dipole moment that occurs when we have two polar molecules and a polar shape. So don't forget that. If I have something like, say, HCO double, so it sounds like formaldehyde, HCH double bond O. This CO bond creates a partial positive around the oxygen and a partial negative around, partial negative around the oxygen, partial positive around the carbon. And this can then be attracted to anything else that has a dipole, or it can even induce dipoles in other molecules. Now, hydrogen bonds, which are the next thing closest to ionic, is when we have an HF, an HO, or an HN, and there's another N, O, or F. So this guy does not have a hydrogen bond. But formaldehyde could hydrogen bond to water because water does have an OH bond. It could hydrogen bond with ammonia because ammonia, NH3, does have a NH bond. It could hydrogen bond with hydrofluoric acid because it does have a HF bond. So anything with an OH can hydrogen bond to anything with an oxygen, nitrogen, or fluorine. It doesn't have to be within the same molecule. It helps, but it doesn't have to be. But these forces are the key things that result in all the different weird properties of solutions.